All the all
Well,
the all the Facebook forums are gonna start roasting the stuff I just spent 6 months working on. It's always fun. hmm
well, cool. What time is
Do,
it? Oh,
wait, do we want to test screen share real quick?
yeah, try that out.
Okay, let's go. And then if I switch to this, you can see this okay?
Yeah. Oh, that's yours.
Yeah,
Okay,
yeah, it's my,
never
oh
mind.
yeah.
No, no,
Hmm.
you're good. You're good. Don't worry about it.
Okay.
I thought it was me for a sec.
Okay, cool. All right, so we got this guy here, and then if I pop out here, you can see all that.
Yeah, and I'm gonna change it to this. I think.
Let me try. I'm gonna try something
I
real
don't want
quick.
that. No.
Let's see if I go like if I go like there and then pop out and then go back in.
All right. I'm trying to make him still so you can see him like easily. Is this good size? Should
Yes.
yeah? All right, we're gonna leave it like that. Cool. All right. Well, that looks good. I think we have everything set up here. Looks like you're good to go.
Yeah.
We're already recording, so that's good.
Yes. Mm-hmm.
Sweet. Well, you kind of have met some of these people, I think, in AES. Have you guys met Nate? Some of you, right?
Probably had a mask on. This is what I look like without a mask.
But yeah, he like came here basically last quarter, vomited a ton of knowledge onto the whiteboard.
Yeah.
It was a total mess, but in the best way possible.
Yeah,
Um,
I also didn't know like what year you guys were, whoever I was talking to, so it's just kind of like I think my problem is my default assumption is everyone knows like way too much because there's just like every once in a while you just meet those people and you're first year, like how do you know this stuff? And so I just have just defaulted to like, well, here's everything, you'll get it, and sometimes it's too much. So today I'm rolling that back quite a bit.
cool. Well, so anyway, so yeah, we've had Nate in the past, but he does not live around here. It's kind of difficult to get out here sometimes. But I reached out to him, told him kind of the stuff that we've been working on, also in like our build sessions on the weekends, and basically just the idea that we're now running into this problem where we're going from these theoretical circuits that we're like whiteboarding to now looking at circuits on an actual breadboard. And it's like you actually have to pick components, you have to actually do these things. So I asked him if he could talk about it. Like I said, he knows a ton. So I asked him to try and limit it, but also make it helpful. And so kind of at his discretion. But what I would say is if you are in the more beginning part of your curriculum, um, always just try and get what you can from this. I've listened to some things that he's explained like multiple times, and then like he'll explain it in the future, and you get something else because you're at that level, and that's so. Look for kind of the things that are at your level and see what you can get out of this. It would be my advice.
And if there's nothing at your level, I'm kind of trying to get this particular lecture accessible to like very entry level, like, and I want to encourage everyone. I'll say this multiple times, but try not today with this lecture. Try not to get caught up too much in the technical jargon. We're really going to be just looking at like things at a high level, and I'll be mentioning some technical things as examples, but don't focus too much on that because this is not really an analog lecture. This is more of a process lecture.
All right. Well, yeah, I guess with that, that's kind of an introduction. If you want to introduce yourself and kind of your background and everything, and yeah,
Yes.
thanks again, man.
Yeah, of course. Well, thanks for having me. I'm Nate Hatch. I work for Fender Musical Instruments Corporation. The most recent mischief that I was up to is I worked on the new Hammertone pedals, which are now available on Sweetwater and everywhere. And I worked on all of them. I did not design them from the ground up, but I kind of got them to where they are. They needed a little bit of help, some polishing, if you will. But yeah, I've kind of been around the block. I started off at Cal Poly, graduated 2019, electrical engineering. That's me If you couldn't guess, that's me. Back in 2018, I want to say, um, when I was first president of the club, ran it for like 2 years. Um, After I graduated, I started working for a microphone company called Countryman Associates. They're also known for their active DI boxes, so kind of like pro audio part of the audio world. And I stayed there for, um, well, I was kind of working for them while I was at Poly. So from like November 2018 to like July 2020, mid pandemic. And after I worked for them, I was a consultant. And then while I was doing independent consulting, Fender reached out to me and was like, "Hey, you want to move to the desert and make music stuff?" And I was like, "Okay." So that's where we are with that. Um, I kind of want to preface some of what I'm talking about today with you guys are gonna have it harder than I did. And the reason for that is because I'm sure you guys have seen plenty of memes about, oh, sorry, I haven't texted you. Supply chains are so bad right now. But supply chains are really bad right now, and that this is especially true with electronics components, and that really kind of makes the process of designing things very hard, especially if you're a startup and you don't have a lot of money to buy, 10,000 of one part. If you're buying like 50 of one part, you can make this design around this very like, okay, this part's perfect for us. And then like a week later, there are none left on the planet. So you guys are going to be dealing with some weird issues, and I just want to make sure that everyone here is aware of that. And that's kind of part of what this is for, is to kind of give you a little insight into like what we're dealing with on the professional side. It's challenging for us too. It doesn't matter how long you've been in the game; everyone's kind of frustrated with this whole thing, and yeah. So hopefully this kind of helps with that. Again, as I mentioned before, try not to get all caught up in the technical analog jargon that I'm going to be mentioning today. The main thing that I want you to focus on again is process. This is a process thing. How do you go about this? What will you expect at a high level when you're picking out integrated circuits? We're focusing on op amps and comparators today as simple examples, but this applies to anything, any part, even resistors, capacitors. There's not just one kind of resistor. There's thick film and thin film resistors. There's 0402 resistors and 0603, and there's kind of an explosion of complexity with any part, literally any part, like traces on a PCB. You'd think, oh, it's just a wire, and it's like, no, there's those traces have resistance and inductance, and so there's all sorts of things to consider with each. So we're going to narrow it down to a couple specific, simple examples today. Yeah, so today we are covering component selection. I'm just going to move right into the overview because I think that's the clearest way of looking at this.
Oh, by the way, Nate, just wanted to interject real quick, just to tell you guys, if you have any questions, just write them down because we should have time at the end for Q&A and that sort of thing.
Yes, I will be going a little fast. Again, bear with me. And then yeah, keep your questions for the end. Think of it. If something comes up, there's no stupid questions here. I was exactly where you were a few years ago. I didn't know anything. I didn't know what a load was. I was like, I didn't know what a source was. I didn't understand how resistive networks paired together and blah, blah. Don't worry about it. Just write down all the questions. So yeah, like I said, 2 examples today. We're going to be talking about an op amp buffer and an open collector comparator. And I will be defining both of those very briefly. Again, today's not about the technical jargon, but I do want you to sort of understand what I'm doing as I'm going through this, because if you don't understand what these two things are, it's going to be kind of whack. So yeah, anyway. And then at the end, yeah, we'll do Q&A. So I'm going to whip through the general approach first. So when you're picking a part, okay, and then again, this is very general. All right, this is, if it sounds extremely general, it's because that is the intent here. It's like this is with all projects. What's your budget? Like, when you're adding up all of the parts in what we call a bill of materials, a BOM, BOM, bill of materials. When you're adding up all the component costs for your device, what are you looking for? Are you selling this thing? Do you not care? Like what is your budget? At some point, you kind of need to add up all the numbers and be like, okay, I want the component cost of this thing to be like $100, $200, and then we're gonna sell it for $500, something like that. right? You need to think about that stuff. Sometimes that's not your job. Sometimes it is, but it's always a consideration. Next thing, and this is kind of what I was alluding to earlier. This is especially relevant now in COVID times. You want to be aware of a part's quantity and availability. You know, like how many do you need in your design? Do you need one? Do you need five? Do you need 50? Uh, you know, it could be op amps. There's some like power PA designs, like the big speakers you see at like live events, and they've got like 20 op amps in there. So, you know, it's like, how many of these things do you need? And it's like, okay, how many of these things do you need? And multiply that by how many of this device you want to make, you know? So if there's 20 op amps in your design and you want to make five of them, you need 100 op amps at least. But you're going to be prototyping, so you need more of that, more than that, right? You don't want to just buy the bare minimum amount of stuff ever. Like, yeah, so if you've got, you know, if you've got 20 op amps in your design, don't buy 20 of them, buy 50 because you're going to blow some up. So don't don't uh don't ever buy it just enough. Buy too many. And so when you factor that in, right, you need to look at um stuff like octopart.com, findchips.com. I'll kind of look at those later, like in real time. But those are essentially aggregators of component distributors, and they will give you an idea of how many of a certain part exists in the American market. Okay, now it's harder to find. There's a lot of stuff that might exist in the Chinese market, and that's a whole other discussion. But today we're going to be talking about what's available in the American market. Um, and yeah, so you kind of need to gauge like what's available. Are there enough of these things on the planet to actually make a design with? Okay. Next, and also all these are not like chronological. You're kind of juggling all of this at the same time. This is not a like one, two, three, four. Notice I didn't put numbers. This is all kind of it turns into a big ball. So, yeah, you want to know what your system requirements are. Like, what do you need the part to do? You know, do you need this op amp to be able to run on plus minus 15 volts? Do you need it to run on a battery that provides you with 1.8 volts? You know, what are you working with? A lot of times it's, you know, you start with like power constraints and, you know, start looking at stuff like noise or whatever. It just depends on what part you're concerned with. Like I said, every part kind of has like its own little universe, and there's like a whole set of parameters you'll learn to be aware of. Nobody knows all of those parameters off the top of their head. It's kind of like every time you look at a part, you kind of go through the process. This is why I'm trying to make this more of a process thing, is because not all, like every electrical engineer has like everything memorized about every single DC-DC converter and op amps and memory chips. Like they all have their own sets of parameters, and there are people that specialize in each of those things. That's why there are teams, right? Is because some people are specialized in this thing, and you'll ask them like, hey, what do I need to look for? And then they'll tell you, and then you look for the thing. Okay. I kind of split up system requirements into what do you need, what would be nice, and what do you not care about. Um, I think that's pretty self-explanatory and will become even more evident once we get into examples. And finally, there's I stole this from Vladimir Prodnov, but I say it all the time. You want to look at trade-offs with your design, and a lot of times this will be like performance versus cost is the classic one. You know, you might be able to find like the best op amp in the world, but does it cost four times as much as an op amp that's almost as good? And so you want to consider like, you know, what's your budget, right? So you see how these things kind of like start molding together, right? And then the other example I gave was, you know, okay, maybe this thing's really cheap, but are there only 10 of these on the planet? This is a COVID thing. This wasn't a thing when I got into the industry, but now it's like you go on DigiKey and there's like 100 left of your op amp. And so you got to think about that. It's like, are you just making a circuit for fun, or are you making a product? If you're making a product, you want there to be at least probably a few thousand. It just depends on how many things you're making, right? Like the other day I greenlit ordering a bunch of op amps for Fender, and when I say a bunch, I mean 22,000. You guys are probably not going to be ordering 22,000 op amps anytime soon, but I hope you see what I mean. It scales depending on how big you know, the design is and the company is and whatever. Okay. So let's get right into it. So our first example is an op amp buffer. Okay. I can kind of see you guys. I'm curious, how many of you guys know what an op amp buffer is? Can I see a show of hands? Okay, we got a couple people. That's cool. No worries, no worries. Well, that's why I have an LT Spice demo. Okay, so check this out. So I'm assuming you guys know what a voltage source is. That could be a battery, right? This is the voltage source. It could be a battery, it could be a guitar pickup. In this case, I'm going to consider this kind of a guitar pickup. That's what this voltage amplitude is modeled after. So the green trace here represents what's directly coming out of the source. Now, every source has something called output resistance, which is essentially, how, can this thing drive a speaker or can it just produce a voltage? You would never hook up a guitar pickup to a speaker, not because it would blow anything up, but because nothing would happen. It's not designed to drive current, it's designed to make a voltage. So you have an output resistance here. So let's say I have a low output resistance and then like of 100 ohms, and then kind of a medium-ish, kind of lowish load resistance, input resistance of 1K. This is a voltage divider, okay? So this blue trace right here is the voltage that comes from, well, it gets divided. Some voltage gets dropped off here at this resistor, and the rest gets dropped off here. So you can see the blue trace is a little bit smaller than the green one. Now let's say it's more like a guitar pickup. Guitar pickups oftentimes will have around 10 kilo ohms of output resistance. So what happens if we try to drive a load with that much? Look how much the voltage shrinks. So again, this is the voltage you want, and this is the voltage you get if you're not careful. So this is where op amp buffers come in. Okay. So check this out. We're gonna move this over just a little bit. Okay, we're gonna put this guy here. Oh, sorry about that. Okay, and then I'm gonna connect the output here. Okay, and what we're gonna do here, I'm gonna close this out, run the sim again. All right, so again, this is the voltage we want. Okay, now you remember before when I didn't have this op amp here, this voltage was a lot smaller. Let's take a look now. Look at that, same size. So essentially what we're doing is we're making the voltage source that has like a significant amount of output resistance work a little bit less. Your guitar pickups are just not designed to do a lot of work. They don't have any power. They're just making a voltage from having its magnetic field disrupted. So as you can see, the traces are the same size. So that's kind of the purpose of a buffer. Now, there's a lot to think about when you make a buffer. It doesn't look like a lot, like it's just the op amp and then you just kind of loop. You do this little loopy thing here, and you're driving your load and you're like, boom, you're done, right? Well, there's a lot that's not even in this picture. So let's talk about that, right? Let's take a look at what system requirements we have. In a guitar pedal, we're gonna kind of contextualize this. Let's say we got a guitar pedal. Guitar pedals run on 9-volt DC. Okay, and what that implies is that we're going to be doing a single supply design. Single supply means we've got a voltage source at 9 volts, and then the signal will swing at most from 9 volts, and then we'll go down to ground to 0 volts, 0 to 9. And there's a further implication there that we need to bias the signal at the midpoint of that range. And that's almost always true when you're working with analog stuff. There are exceptions. I'm not going to go into them here, but generally when you're working on analog stuff, you are going to bias your signal around the middle of your range. Okay, in this case, I said it was 0 to 9, so the middle of that is 4.5. Okay, and you'd be surprised at how many op amps can't do that. It's not like an easy thing, so that's what we're going to be looking at. I'll be going on a supplier here in just a sec to show you what I'm looking for, but these are the basic system requirements. Okay, for a buffer, this is generally not where you're doing any signal processing, so you want it to be kind of transparent, and transparent usually translates to low noise, low distortion. Noise is just how much of is it making? Because a lot of capacitors don't, but resistors, op amps, amplified, like there's just noise sources everywhere, and so you want to try and with each thing that you add, you want to try and be mindful of like how much noise do I want and yada yada. I'm not even going to get into, excuse me, I'm not even going to get into quiescent current here. I just kind of threw it down because I was just thinking about that. Just some things I'm thinking about. Okay, SOIC8 is just like the physical realization. What is the plastic package with the little spider legs coming off? Like which one of those are we picking? SOIC8 is generally a good choice for guitar pedals because you can get 2 op amps in a small case, and yeah, they just don't take up a lot of room. I think the best thing to do here though is, so I did my little demo. Now what I'm going to do is I am going to look at, actually real quick before I jump on DigiKey, So this is an outline that I did for this lecture, and I think some of it may actually be useful to you guys. So I'm just going to provide these notes at the end. So this right here is what I'm thinking about for the op amp buffer. Okay, so there's a couple things I want to highlight. Number one, a buffer means that the gain of this amplifier is 1. Now, not all op amps are actually stable at unity gain. Unity gain being the gain equals 1 or 0 dB. Okay, the signal coming in is no bigger than the signal coming out, or vice versa. Anyway, so yeah, not all op amps are stable at unity gain, and then there's a lot of stuff here that I don't really want to get into, but it essentially amounts to we want a FET input op amp. A FET is a type of transistor, and it has certain implications for uses in input stage. I think the most important things would be the high input impedance, which this is an ideal op amp. It has infinite input impedance. The input impedance of FET input op amps tends to be in the giga ohm range if it's a FET. So I mean that's not infinite, but it's pretty big. So that's good. That we want things that are close to ideal, right? But there's no free lunch there. It's nothing really behaves like this exactly. And then the other thing is that the other reason why we might want to use FET input op amps is because they are more resistant to stray RF signals. Because the other choice, which are bipolar input op amps, they sort of act as passive mixers sometimes, not always. Some are worse than others, but FETs, field effect transistors, are more resistant to that. So anyway, what all this amounts to is we want to find something that's stable at unity gain, and we want to find a FET input op amp. So let's get right into it. Everyone can see, right? Alex, can you just give me a thumbs up if you can see the DigiKey stuff? Yeah, cool. All right. So I'm literally just going to type in op amp. Step 1, type in op amp. Step 2, linear amplifiers. Okay, that's what we want. They look at some of these other ones. It's like, no, this is not what we want. This is an eval board. That we're looking at single components here. So this is what we want
Hey,
here.
hey Nate,
Yeah, what's
are
up?
you able to like scroll your Zoom a bit?
My Zoom. I can try. Let's see. How's that?
Cool. Yeah. Does that help, guys? Great. Cool. Yeah.
Okay. All right. Next. This is going to be interesting. Okay, so we're getting right into it. Now, remember I said every single part has its own little universe. Well, look at this. Look at all this stuff. There's a lot of stuff, huh? Well, some of it we don't need. Okay, I don't ever look at these really. Um, I think the things I almost always use, no matter what the part is I make sure the part status is active, meaning it's not discontinued. You don't want to design with a discontinued part. That would be silly. I also look at view prices at 1 because generally when we're prototyping, you might want to buy like 5, not 100. So I make sure that they're available to buy at 1, because you're looking there essentially at something called minimum order quantity, MOQ. And that's like different. Some websites will be like, you can't buy 1, you got to buy 50 of these. So that's why I put this little 1 here. I want to make sure they're in stock and they're normally stocking it. Okay, so that's kind of what I do for everything. Okay, next, I do want to quickly note that there is a JFET option here, but some manufacturers don't actually mark down that it's a JFET amplifier. So we're not going to pick that. We're actually going to go 2 circuits here, and 2 circuits means there are 2 op amps in one package. Okay, that's all that means. So if you hear dual op amp or quad op amp, it just means there's not like a crazy thing going on. It's literally like 2 op amps or 4 op amps. In this case, we're looking for dual op amps. Okay. There's some stuff that's kind of advanced analog over here, and I'm not going to get into it. What I will get into though, here's a little hack for you guys. If you're looking for FET input op amps, you're going to want to look at the input bias current. So input bias current for bipolar op amps is going to be in the nanoamp range, nanoamp to microamp range, and it's going to be picoamps for FET input. So what we can do is kind of look at where the break point is. Like, okay, there's like 600 picoamps, and we'll scroll all the way up, and then just select all of that. Oh, that's not what I wanted. Hold on a sec. Shift click is your best friend here. Let me. There we go. Okay. All right, and then we want to look at the supply voltage, right? So um, we want the this is a little confusing. We want the minimum maximum value to be 9-volt single supply, right? Look at that. It's not. It's kind of grayed out. So I mean, any of these will do. We don't really need an op amp that runs at 80 volts, but you know what? We'll throw it in there. Why not? And then we mentioned SOIC8, which means it's going to be surface mount. Surface mount means it sits flat on the PCB. It does not have legs that go into holes like on a breadboard. It's flat. So this we're looking at surface mount stuff. Okay, and look at that. We narrowed down. I didn't see what the original amount was, but it was probably in the tens of thousands. We narrowed this down to 276 op amps already. Okay, so we're gonna hit apply all, and then let's look at what we got. So by default on DigiKey, I'm so glad they did this. I'm not gonna say they did it because I gave them a lot of feedback on their website, but it's pretty nice to have this as a default. Anyway, so they have this sorted by price. Okay, so if you notice now, we did that input bias current thing. Look at that. Every single thing is JFET 2 circuit. That's what we want. Okay, and I didn't select SOIC8, but a lot of these are. That's what SOIC8 is. It's just it's just a flat. It's just a thing. It's a block of plastic with a circuit in it, and it's got little spider legs coming out that allow you to connect to the internal circuitry. Okay, so okay, 42 cents at quantity one. That's cool. It's the cheapest one, but look, there's 833 of them. That's not that many, right? But then we look at the next option. It's a little more expensive. It's 8 cents more. Not too much, right? But it is a price increase, and that can add up if you're using 20 or 40 op amps in your design. Okay, price increase, but there's 20.7K of them available. Sounds pretty good. Why don't we take a look? And so what I'm going to do next is like, okay, I mean, a lot of the stuff that I care about is already here. It's a JFET amplifier. It's SOIC8. It's a dual op amp. Okay. Um, so we want to take a look. Okay, look at this. So the minimum voltage that this op amp can run on is 6 volts, and the maximum is 36. That meets our requirement. 9 volts is right in the middle of that. Perfect. Okay. Now, typically, I also look at the data sheet as well, because there's some things that are not on there, namely namely the noise. The noise is not really listed here, so I'm just curious. I want to see. By the way, this is what the inside of an op amp looks like. That might mean nothing to you, and that's okay. It doesn't matter. Dual op amp. Remember, they're both. There's just two of them in one box. Okay. Um, and okay, we got our supply stuff there. Yada yada. Also, if this looks intimidating to you, it's really not that bad. You just have to read 10,000 data sheets and then exactly 10,000, no fewer. You have to read 10,000 data sheets and then you will understand what this means. Some of it will never make sense. There's stuff in here I have no idea what it means, but I understand a lot of the relevant stuff. You don't need to know everything to make a good design. Okay, you just need to know there's just a few things. You need to know what the few things are, and you can if you guys are having trouble, you can hit me on Slack or email or something. You'll figure it out. You'll start to get a feel for it. It's not that scary. Anyways, I want to find noise. Does it list the noise? Here we go. Look at that. Equivalent input noise voltage, 15 nanovolts per root hertz. That's good. That's fine. Now, you don't have a frame of reference for this, and that's okay. But I'm telling you, it's good. It's fine. Total harmonic distortion, 0.01. Also okay. It's not the best. There's stuff that's like 0.000000001. But they're kind of in low stock right now, so we don't care about that. We want to make a thing, and there's 20,000 of these available. Boom. Pick this one. So again, it meets our, sorry, I keep going back to that one. It meets our system requirements. Let's go back to what those were. System requirements were 9-volt single supply. This thing runs on a range of 6 volts to 36 volts. It's got some good low noise, and it's low distortion enough. Again, not the best, because there's stuff that has 0.0000001% THD. This one has 0.01%. Yeah, it's fine. Whatever. Low quiescent current. I didn't even look at that, and you know what? It's not even worth getting into. And it's an SOIC8 package. So there you go. That's how I do it. And kind of to quickly recap on what the strategy was there. We were looking at, let's go back. Do we use our general strategy? What's our budget? We didn't talk about that, but We just found like the second cheapest thing, so we're gonna assume it's okay. Quantity and availability. We didn't really talk about how many we need. We need one. We need one in our design, right? We're just doing a op amp buffer. Um, so not a huge concern there, but the availability is what we looked at, right? Because the first one we looked at had 833 available, and the second entry on DigiKey had 20,000 available. So that's like, okay, we got some there. But don't sleep on it. Don't be like, oh, there's 20,000. It's gonna be great. Check back tomorrow because they might be gone. Toyota might have bought all of them. It happens, like really often. Like I said, like we greenlit a purchase for 22,000 op amps at Fender, like a couple months ago. So keep on your toes. Don't feel like not everything's like fair game. These big companies will come in and they'll just eat up all of them. And yeah, so I think we used our general strategy pretty good. Our trade-off was the one trade-off we looked at was, okay, this is cheap. It's a little more expensive than that other one, but there's more available. I suppose another trade-off you could think of is this is a pretty cheap part and the distortion performance is not the best, but not to worry about it. It's good enough. A lot of times you'll need to say good enough on some part of your design. Okay. So next thing, we're gonna look at comparators. Okay, I want to see a show of hands again. Who knows what a comparator is? Okay, kind of like same
We got a
same.
little more this
Got a
time.
little more. That's very interesting. Okay, so for the uninitiated, the comparator, unlike the op amp, has an analog input and a digital output. I mean, technically everything's analog, but functionally speaking, you can have a range, an analog or infinite number of voltage values going into the comparator, a well-designed comparator stage, and then the output has two states, high or low. Okay, it's like a so the application that we're going to be doing here is kind of a we're gonna take so looking back here, now that we have our op amp buffer set up, like in if we're looking at LT Spice here, okay, we've protected our guitar input here. We want to take this signal and do something with it now. Okay. And so what we're going to do is we need a microcontroller to take a look at it and do some digital magic with it. But it only happens when this voltage here, what I'm gonna do is hold on, let me delete this. Okay, there we go. That'll make it a little clearer. So when this voltage hits a certain value, we want there to be a flag. We want there to be like, do something now. So what we're gonna do is we're gonna use a comparator to signal this microcontroller. Now, let's look back at our system requirements here. So again, the supply voltage that we're working with, it's a guitar pedal, so we're working with 9 volts. Okay, but we're interfacing with a microcontroller. Microcontrollers run on a range of voltages. Some of them run on 3.3 volts. That's a different voltage than 9 volts. You don't want to run a 9 volt input into a 3.3 volt device because it's not designed to handle that. You could harm your device. So that's where there's a number of devices that come in, but the simplest one is a comparator. And in this case, we're going to be looking at an open collector comparator. Okay. So what is that? What is an open collector comparator? Don't worry about all this crap. This is the comparator. This is it. This is really what we're focused on. Notice this is a transistor here, and notice that it's kind of just hanging here. This is the collector right here. It's just a part of a transistor, and it's open. What does that mean? Well, it means we can kind of shift around voltages. We could have a voltage that's running in here like 0 to 9, and then we can attach a load here going up to 3.3 volts. And what that does is it kind of level shifts stuff around. We're sensing stuff in the 0 to 9 volt range, but we want to shift our logic down to 3.3 volts. Our logic being high or low that we're feeding into a little computer. Okay? So again, don't worry about this M here. I think they're saying this is a motor. This is a resistor for what we care about, and we're just gonna hook it up to 3.3 volts. So we're like kind of doing a little bit of a level shifting or voltage interfacing is what you might call it. Okay. I'm gonna try and be done with this example a little quicker so we have lots of time for questions. But essentially, that's what we want to do. We have our guitar signal coming in, and we want the microcontroller to do something with it. Once it's like here. Okay. And so, all right. So we need this comparator to run on 9 volts. And that's pretty much it. It's kind of it's a little less stringent than going the other way from running on a lower supply voltage and maybe doing like an LED at a high voltage. This is a little bit of an easier example. Okay, so what we're gonna do is we're gonna go DigiKey. Here we go. Is it zoomed in enough?
Yes.
Okay. Oh, I'm in all caps. You know what? Screw it. I'm gonna comparator. There we go. uh, there it is. We want linear. Okay. Now logic is a little bit different. We're not going to get into those today, but remember I was talking about it has an analog input and a digital output. That's where we're going. We're going here. Okay. Remember what I was doing last time? It's the same thing. Active, quantity one, in stock, normally stocking. Okay. Look at that's funny. 1,234 remaining. Okay, so we're gonna apply all our current filters. Okay, so we got 1,234. We don't need two. We just need one. We just need one comparator. One. When it says number of elements, it just means like you remember when we were looking inside this guy? There's two elements. It's two circuits. So you might see circuits or elements is the same thing. Okay. Anyway, so we want one comparator in one package, and I kind of don't care what package it is, but I do want it to be surface mount. Okay. So, the supply stuff is a little annoying here because all the all the manufacturers make it a little different. But 1 volt to 5.5 volts isn't going to work, right? Uh, but this one would because 9 volts is in the middle of that. So we kind of have to go through and control click a bunch of these. It's a little silly that you have to do this, but okay, that one will work. That'll work. That'll work. That'll work. Again, we're looking for a nine something that'll run on 9 volts. All these things work here. That'll work. That'll work. That'll work. That'll work. Oh, sorry. That'll work. How many do we have? We got 83 remaining. Okay, let's do a few more. You got 85 remaining. So we narrowed it down to from 1,234 to 87. That's pretty good. That's kind of what you want your goal to be. You start with a bunch of parts and you're like, how many? Okay, when I have this many filters, are there like 10,000? Okay, I probably need to narrow it down a bit more. And then you just shave it down and well, look at that. We're at 87 now. How many does that give us? 100. Okay, that's pretty good. Let's see what we got. Apply all. What we got? Okay, so kind of around same price range, right? But 171 of these bad boys. It's not a lot. Um, so yeah, we want to take a look at what else we got. Look at this guy. What's this? What's this guy? TL391. Okay. Is it open collector? Look at that. It is. 2 volts to 36 volts. Very good. Very good. Um, we're not really driving any current because we'll probably have like CMOS digital inputs, so 20 milliamps is fine. It's surface mount. Okay. This is looking promising. Let's look back at our system requirements. There's not much. It's we're going from high to low, which is easier than going low to high. So our again it works up to 36 volts, so 9 volts is a-okay, and we're interfacing with 3.3, which means it's open collector, which this thing is. It's open collector. Let's take a look. Let's take a little bit of a closer look. What we got here? Lots of stuff. We don't need to really get into all this, but there's one element, right? And we have recommended operating conditions, supply voltage 2 to 36. Our conditions are a little less stringent than the op amp. Remember, I was saying this is all the crap that I'm thinking about when I'm looking at an op amp buffer. But with the comparator, this is what I'm thinking about. You might see a lot of 311 type parts around. Don't worry about that. That's just kind of a random note. But anyways, this guy's looking pretty good. Okay, so once again, let's go back through our general strategy here and let's see what we did here. Again, we weren't really looking at budget too much, but we kind of found like the cheapest thing. That's almost always what you're gonna do. That's what everyone does. You just go to your thing and you hit the up button on the price. So you start with the lowest price and it goes up to the highest. It's a cheap part. It's 50 cents. It's probably fine. Quantity and availability, again, that was something we looked at because we had the cheapest option. There were only 170 of them available. So we went up to the next thing. It's a little more expensive, but there's more available. And there's your trade-off also, right? Is there's more available, but it's a little more expensive. You're going to see that a lot. You guys especially are going to see that a lot, so just be prepared for that. Um, there's a lot of like what would be nice, and but there's a lot we don't care about with this thing because it's digital interfacing and it's going to be pretty low frequency. We're not dealing with like gigahertz, peak detection or something like that. It's audio's 20 to 20K, and guitar falls in an even smaller range than that, and that's considered very low frequency. So there's not really a ton of requirements here, you know. So anyway, we met our requirements, right? We all it was it needs to run on 9 volts and needs to be open collector, and so we did it. Um, so that's kind of it for the examples. Now get into Q&A. I want you guys to feel free to pull me back to any part of that process I just did because I did go really fast, but I went fast because I want you guys to ask questions here. So, yeah, hit me. Let's go. Oh, and as it says, take a second. I also didn't know what questions to ask a long time ago, but just try something, and then usually when one of you asks something, someone else gets the courage to do it. So go forth.
Timeline for a process like this to happen from ordering to like how long does it take for the parts to get there and then for you to actually be working on whatever circuit or device and like then completing that circuit and then like how does that fit in with deadlines for your job?
Did you catch that?
I caught parts of it. Alex, could you repeat that for me?
It was basically what's the timeline from like tell me if I get it wrong, but like when you place the order, like when you choose something, and then you get the parts and you get to start working on it and that sort of thing.
Plan and then like and then into deadline.
And also, I guess getting into like deadlines, like how that affects how that
Sure.
kind of plays a role.
I mean, the way project timelines are going to be set up is highly dependent on what company you're working for and your manager and all sorts of stuff. In terms of how long does it take for the component to get to you? That depends on how much you pay for shipping. It's just like anything. Uh, so if you want the thing tomorrow, you can have it. You just got to pay for it. So yeah, it kind of depends on where you're at in the project. Like if, suddenly we're like, oh no, we need to replace this part and this thing is going out to market. I'm gonna want this part tomorrow. So we'll spend the extra money to get it to me. And in terms of like deadlines, that's highly dependent on what circuit it is and how, if I'm modifying something, am I starting from scratch? It's kind of, where are we at in the process? So if I'm earlier in the process and the design is not necessarily well defined, it's going to take a little bit longer because I'm still trying to define things more. But if the design is well defined and I'm replacing an op amp, we pretty much just need to have a circuit and then I desolder the op amp and put in a new one and go, does this do the thing that we want it to do? Cool. So it just depends on like, am I starting a design from scratch? Am I modifying an existing design? And what is the design? Is it an op amp or is it a DSP chip? Or is it an analog to digital converter? Highly integrated stuff. Those things are harder to test. And they're also harder to redesign for, which we had to do. We've had designs where we needed to take out an existing ADC and DAC and like replace them because there was like a factory fire with one of our like Japanese manufacturers, and so we had to redesign stuff. So yeah, that one took a while. It was very hard and expensive, but there's other things that require redesigning and it takes less time. So the answer is it depends. So hopefully that was helpful. Other questions?
What's like delays look like when you can't find the parts that you want? How long do you usually have to wait? How long is it usually set back?
Yeah, so the question is basically what do delays look like when you like need to find a part or you can't find a part? How long like is that setback and how do you kind of handle that?
Okay. How does it delay us? Well, ideally, we don't want it to delay us. So there's kind of some tricky situations going on right now where we've got a part that we made a design for, but there's barely any left on the planet. Um, we're trying to find some for prototyping. We don't need that many. The minimum order quantity one thing is like a lot you'll do that for prototyping a lot. But for production, we want like thousands of them. So like with this company, we can be like, yo, we want to kind of schedule ahead of time. Like we're gonna use like, you know, 40,000 of these a year or whatever, more probably. Um, but we tell them that ahead of time and we can kind of set up that order now, but it's a different challenge entirely than trying to get some right now and we only need like 10 of them. Um, so that's like there's just a lot of different kinds of delays. And really the thing is we don't want delays. We want to be able to order the things now. It just depends on, did we do this extremely complex design around a very, specific part like a Class D chip, a DC-DC converter, an analog to digital converter, a digital to analog converter. All of those require a lot of, big brain jumping through hoops, and you're like, okay, I've got this design done. And then when you're done, sometimes there's nothing left. And yeah, so in terms of like delays, uh, the thing right now is that the delays are kind of not well defined. It's kind of like, well, we'll get them to you when we can, but right now, chip companies like TI, Diode Zinc, ON Semi, they're all in line for fabs. The people that are actually making these integrated circuits. There's like a big line, so the fabs are pumping out everything as fast as they can, but it's kind of whenever they get around to it. So because of that, because it's kind of whenever they get around to it logistically, we want to get stuff that's available now. That's my best answer for that, I think. More questions?
Do you verify the quality of the parts that you're receiving and that everything on that data sheet is true to what they say? And that the part that you're buying doesn't have a higher rate of defects or something like that. How do you judge that?
I think I caught most of that. So how do we judge the quality? Well, there is. I personally am not a huge fan of brand loyalty, but in the semiconductor industry, it's kind of a thing. And it kind of depends on what type of part you're looking at. In terms of the quality and consistency of something, it depends on, again, depends on what kind of part you're looking at. So for audio op amps, if I had all the supply in the world, I would go to TI because TI makes the best performing parts at the best price. Always. That's like always the case. The problem now is that because of that, the demand goes up, supply goes down, and now there's not a lot of those left. So you kind of are stuck trying to find what's left. Um, so yeah, there's kind of some, a little bit of like, hey, TI is cool. Oh, Diode Zinc is cool for DC-DC converters. ON Semi is cool for DC-DC converters. And this is not like an official Fender endorsement. This is kind of just like facts. This is just like if you go, go out, you're like, I need a DC-DC converter, just practically speaking, like Diode Zinc, it's like, oh, yeah, like the Diode Zinc or on Semi, there's going to be companies that specialize in making things that are performance at the price point. But in terms of consistency, because of the technology that's available nowadays, most things are going to be pretty consistent, but there's going to be a spread. There's always going to be a little bit of a Gaussian spread in terms of this op amp might be a tiny bit noisier than its brother, you know? And a lot of times those tolerances are okay. Sometimes they're not. And for certain components, like, okay, so let's say I'm setting a voltage rail with a DC-DC converter with a resistive feedback network. And I want that voltage to be the same. Those resistors are going to fall within a certain tolerance range, right? You're going to see stuff like 5%, 2%, 1%. And if I'm really picky about wanting this voltage to be exactly right, I'm going to use, 0.5% or 0.1% resistors because that just means there's a smaller spread of resistance values. Okay, and that sort of logic applies elsewhere. But that was like the simplest example I think of. I think generally though, consistency is not a huge issue anymore because um, fabs are high tech, man. That it's kind of where we're at nowadays. I mean, everybody's making pretty decent stuff. I mean, I name dropped a few companies because that was just what came to mind, and it might be helpful to you guys. But again, that's not necessarily endorsing them. There are plenty of other companies out there I'm not thinking of right now, and they're making stuff just as consistently. It's just you might associate one brand with like, oh, this is like, this is what they specialize in. And TI is like audio op amps. They've got like an audio thing and they've got it dialed, and so that's typically who you go to for that kind of thing. Bit of a long-winded answer. Hopefully that's helpful though.
Cool. Well, awesome. I think we're basically at time, so we're about to get kicked out, I guess. But
Okay.
Thank you, Nate. This was super, super helpful. My thanks to you for taking the time to do this, and also everyone at like Fender and just for supporting this. Yeah, looking forward to maybe having you back for another topic, another big brain dump.
Absolutely. So let's get like an email together. You guys are free to Slack me. I'll be slower at responding to those, but you can email me and you'll get a faster response. Feel free to email me with anything you guys got.
Cool. And then I will post this stuff onto the Slack. So if you're interested, you can look for it there. Awesome. Thanks again, man.
Thank you.
Absolutely. Take care. Bye.
Bye.